Well, thank you everybody for coming. Thank you for the introduction. So in my lab, which is actually right below your feet, we study something called atomic physics and produce samples of ultracold atoms. So really we're motivated to study atomic physics because we want to study the very fundamental interactions between atoms, which really means like we want to study the quantum mechanics of atomic collisions. Okay. And we want to further exploit this, our ability to understand and control these simple properties of atoms to create extremely delicate states of matter, the things that I said can't exist anywhere else in the universe. Unfortunately, the fact that at any temperature that's not zero, you have all this random jiggly motion, particularly at room temperature, this motion is quite violent. We find the need to cool these atomic samples down to nearly absolute zero. And to give you an idea of what absolute zero is, we're going to take a trip down this logarithmic thermometer here. And we're going to start up at the top around 1500 Kelvin, which if you are celebrating someone's or something's 50th birthday, you might use some candles that have a temperature of about 1500 Kelvin, where the average thermal speed of the particles in this plasma is probably somewhere around 1,000 meters per second. Now, the first step to making something cold, you might think, is to take it and dump it in liquid nitrogen, which is around 77 Kelvin, but unfortunately that's still way too hot. You might have heard about Google's beautiful example of quantum supremacy, or what they claim to be quantum supremacy, and they took this beautiful little processor guy and stuck it in some liquid helium and got it down to 20 millikelvin, and they're definitely doing quantum stuff, but that's still not cold for us. We need to get down to 100 nanokelvin, where atoms put on little hats and emit. And to do that, we actually need this very large apparatus, which is, as we speak, every 10 seconds or so producing a sample at about 100 nanokelvin. Now it looks very complex, but if we zoom in on this little viewport here, we can see this little blue cloud. And that little blue cloud is actually about 10 million strontium atoms. And they're being suspended inside a very high, or very low pressure vacuum chamber by a combination of 6 laser beams that are constraining their motion in all directions. Once we get them down to that pretty cold temperature, we then trap them in a very intense laser beam. So now we can't show you pretty pictures anymore because you can't see it. But once we get them in there, we end up with about 1 million atoms at 100 nanokelvin, which means we have about 100 nanometers between these particles. And this all sounds very complicated, but this is actually just the beginning to where we start to do the fun stuff. So by fun stuff, I mean we can take these atoms and start shining lasers on them. And what we do, in particular in our lab, is create something called a Rydberg atom, which is named for this guy, Johannes Rydberg. They were discovered in the late 19th century. And what this does is it takes a normal atom, which has a diameter or radius of about 0.2 nanometers, and promotes it to this massive size. So now this electron is anywhere between 100 nanometers to 1 micron away from its nucleus. And at 1 micron, you're talking about almost the size of a human hair. And what's really neat is by adjusting the frequency of the lasers that we apply, we can actually change the size of this orbital. And now if we think about what I said before, where we have our samples at ultra-cold temperatures very close together, we have about 100 nanometers between these two atoms, I can promote one of them to this very large orbital, and now we can see that my electron is kind of starting to overlap with this atom. And this scattering process is actually attractive. And creates a new kind of chemical bond, which can create a molecule with a bond length that's the size of this orbital. So we're talking molecules with 2 atoms that are 100 nanometers apart. And I can make dimers, trimers, tetramers, even pentamers of this shape and size. And this new kind of bond is called a Rydberg molecule. But what's very beautiful about this is that this molecule has a tunable bond length. And the same way that we just change our frequency and we can make molecules of varying sizes. And I mentioned earlier that we make extraordinarily delicate states of matter, and if our temperature was above 1 millikelvin, this thing could not exist. It would just be ripped apart by thermal energy. So we can take this a step further and start thinking about even more particles, even more atoms in this little scheme here. And we can excite one to an even larger orbital, and now we actually enter this regime where we have this massive electron orbital and all of these other atoms contained inside. And what happens is now we really have this crazy situation. This definitely could exist anywhere, except downstairs. So we have this massive orbital and this ion here that's talking to all these other atoms. And what that gives us is a a little interaction where these atoms are pulled in and start colliding with the ion, and they can do all these crazy things, make ionic molecules, and send this electron into a crazy new orbit. And this is really what we're talking about when this is happening is ultracold chemistry, chemistry at the most fundamental, basic level. And that's happening literally right below you right now. Every 10 seconds or so, we're firing the lasers and doing all that stuff. So if you want to ask me any more questions about it, feel free, but that's all the time we have for now, so thank you.